Greetings. Today, we want to present CI's level set discrete element method, effects of lateral melting, and breakage. So just as a brief motivation for this presentation, as we're working with the granular nature of CIs, so the objective is to apply the knowledge of this granular nature in order to explain the more macro scale global planetary behavior of what is going on with CIs, especially at susceptible areas. And of course, our starting point is this global temperature increase that we are having and how it's causing a net loss of CIs. We may have some recovery during the winter, but year by year, we have a reduction in the total area of CIs, which is resulting in changes in albedo, salinity, ocean and wind currents, and many other factors, which are resulting in greater amount of climate alterations, which will then cause a further temperature increase. And at the heart of this problem is the topic of sea ice mechanics. And one of the main questions that we have for sea ice mechanics is how for example, the granular scale can play a role in predictions such as the following: the disappearance of summer sea ice as early as 2035. But at the same time, on this same paper, they imply other models with slightly more long-term estimates, almost to the end of the 21st century. So this level of uncertainty could be reduced or at least resolved if we use models that have a better understanding on the behavior of CIs. So that's the motivation for this presentation. So one of the models that we have developed in our group is the level set discrete element method. And in this case, this is being adapted for the simulation of CIs. And I just want to explain the main building blocks of all the other results that I'm going to show you on the rest of the presentation. So using the level set discrete element method, at its heart is working with level set objects or level set functions, which are functions which work kind of like a topographic map, a watershed, or contour map, in which you have a grid distribution of a attribute or level set function, and the zero contour or zero value that comes from this level set interpolation is considered to be the edge or the border of the grain, particle, or sea ice flow. Values greater than zero are considered to be outside, and less than zero are considered to be inside. It is even possible to track other contours on the inside or the outside of the grain, but obviously the zero contour is the most important for contact and for other boundary conditions related to this level set discrete element method. And the advantage of working with these level set functions is that you can work with any sort of arbitrary wind shapes. They don't have to necessarily be regular geometric shapes. They don't even have to be convex shapes. They could be completely concave. And you can also track or modify the evolution of these shapes over time. It is relatively simple to introduce grain breakage, and you can work with a wide range of grain sizes and tune the resolution of this level set field to have a higher efficient use of computational resources. So we start with this geometric level set, and we're going to have an equivalent temperature level set twin. So it is going to work on a similar way as the geometric level set, but we're going to keep a register of the temperature within the sea ice flow. And what we're going to do is to handle the melting temperature as the zero, as the contour for our level set resolution. So as we're applying melting, and this melting can progress through the boundaries of the level set, there's going to be a coupling between the geometry and the changes in temperature. And given that we have more space, we could even do the opposite and melt or increase the surface area. Or we could do the same thing for thickness. And at the same time, we're gonna handle the evolution of heat using a 2D parabolic partial differential equation, and we could apply different sort of boundary conditions. For this problem, for the problems of this presentation, we just work with Dirichlet boundary condition at the edges of the flow, just for simplicity. An additional element that we include with this is a stress level set or mesh, which I'm going to show more information at the end of this presentation. And this mesh is characterized because you can track the position of the forces from the contacts that are mediated by the geometry and the geometry that is changed by the temperature. So we got like all these different forces acting on our flow, and we assume a breakage surface on the 2 points of maximum force. Of course, we can apply a von Mises or a Tresca criterion to find if the stresses are above a certain yield stress, and though have a separation of this single flow into two flows, which can then melt and have their own particular geometries and evolve on their own, and so on. And then we couple everything of the problem at the same time. The final building block for this is adding the fluid drag, which could be not necessarily water. We could include air or other fluids affecting our flows. And for this presentation, we're going to just to show a one-way fluid to solid coupling, which uses the skin drag and form drag areas and coefficients in order to apply forces on our flows. This is the equation for water, but there's also a slightly modified equation for air. So now that I have explained the building blocks, I'm going to show you how we applied all this mechanism in order to model or simulate the behavior of sea ice with DEM. So what we did first was just like to choose a arbitrary spot here around Fram Strait and just extract like simplified shapes from satellite pictures and simulate the kinematics using a very simple like vortex field. So we can track the forces from intergranular and fluid drag. And interesting things that we can observe on this very simple simulation is how the edges or corners of sea ice play an important role in the contact interaction with other flows, and also how having an irregular geometry can affect the way that these flows rotate or interact with each other, how contacts change given these rotations, given these corners. And this, of course, could give some additional details that might be lost if we use only approximate shapes rather than shapes based on sea ice that we can observe on the field. And as you can see, we could have like very elongated or very sharp sea ice grains, or even those that are formed by the centering or melding of one small flow with a larger flow, and so on. So then we decided to take this sort of flows based on satellite pictures and apply the functions that I explained at the beginning of the presentation. We can apply lateral melting, or we could even apply freezing to induce growth on the flows. And this melting can be applied up to completely disappear some of the flows. Also, it is also possible to induce breakage as even arbitrary points and then couple breakage with the creation of more flows which melt, which can break as well, and so on. So this was just to showcase the properties that I've showed previously. So now we decided to apply a more like practical implementation. And what we did was just to exert a constant ocean temperature field around a set of sea ice flows in LS-DEM. And what we did was to measure the current area divided by the initial area of ice on the system. And we just assume a constant thickness. So here area will actually represent volume or mass if we multiply by the density. So what we decided to compare was this evolution of initial area, the current area divided by initial area, and how the flow size distribution or granular distribution affected the velocity at which we lost CI's mass. So here you can see the results for a polydispersed distribution, in which we have larger flows and smaller flows in between with a relatively soft texture on the sides. And then we decided to compare working with a monodispersed distribution with perfectly circular flows. So here you can see how we have a higher mass rate even with initial conditions that are the same. And as we increase texture or irregularities, even by having the same mass or aspect ratio, we see that this increased surface area will also result in an increased loss of mass. And as we kept increasing the aspect ratio and rugosity of the surface, you can see that we have more and more mass loss, up to a point where elongating starts having diminishing returns. But the takeaway from this slide is basically how the role of shape can be significant in affecting the amount of mass loss that is going on, and how getting like more realistic, more in situ shapes can account for more higher results of mass loss in predictions. So even if we have a realistic looking distribution with very large flows, given the presence of small flows on it, we can have a higher mass loss even for smaller flows with a more regular distribution. So basically, larger surface area will increase melting rate. And that is something that we could capture using LS-DEM. Now, something interesting is here we just have like constant melting. We didn't have like a lot of additional changes. So then what we decided to do was assess for the role of breakage. So we decided to apply a random breakage frequency on the same distribution of flows. And we found out that fracture frequency is proportional to the total melting. So as we increase the frequency of fracture, we had also an increase on the total amount of melting. So of course, these effects of breakage and shape can couple together into the effects of lateral melting. Okay, so now that we have seen like some basic applications, we decided to implement our framework in order to simulate an initial approximation of the Nair strait and work with more arbitrary boundary conditions for CIs. And this is because the Nair strait has been subject of study from various recent papers, and also from some people actually participating in this workshop. So we wanted to explore the potential we could get from the application of LS-DEM. And especially it caught us our interest, the fact that some recent research, like even as recent as 2021, was analyzing the sea ice arc collapses at the entrance of the Nair Strait. So basically, this paper studied like satellite pictures and how, as oceanic forcing, temperature forcing, atmospheric storm forcing started affecting the free stress boundary conditions of these arcs that form at the entrance of the strait, you had like this collapse and flow of sea ice into the strait, and the loss and the complete loss or erosion of the sea ice that was forming, of the monolithic sea ice that initially was present here. And this is also similar to a granular phenomenon such as jamming at a funnel. So we wanted to see if we could replicate this sort of phenomenon, especially given that Nair Strait is relevant as one of the last bastions or last shelters for sea ice to be existing during the summer. So what we did was analyze some recent satellite pictures, and we went over different pictures of the Nair Strait. And we decided to work with those that focus on having like more distinct or discrete objects for the different flows of sea ice going through the strait. And what we did next was to do some image processing of the Landsat pictures to binarize the sea ice from the surrounding ocean, or to binarize the land boundary conditions from sea ice. And we end up getting these ice and land geometries. So here, what we decided to do was just apply a simple condition of all of these sea ice going to transverse through the strait, and just changing different conditions, both intrinsic to the model and through the currents that were related to the flow of these sea ice. So as you can see, here we have the boundary conditions of land, our sea ice, and what we're going to apply on this initial simulation is a homogeneous current in such a way that the sea ice can go through the strait. And what we decided to do as a control of the presence of jamming or friction at the borders of the strait, we'll set up this imaginary line and measure the amount of mass that transverses over time. So here we can see how as sea ice starts accumulating at the onset of the strait, we get to a point where there's jamming and no more significant amount of mass can transverse through this line, unless there are some changes in external forcing. And that's what we wanted to demonstrate using this sort of simulations. So now, instead of just working with the simple sea ice kinematics without any breakage or melting, then we decided to replicate exactly the same behavior, but with breakage caused by contacts with the floes and the walls. And as you can see, this breakage lubricates the mass flux through the strait. And we get to a point where jamming doesn't happen, where this doesn't continue like this, but we have continued flow through the strait. And furthermore, even if we increase the flow density, you can see in the prior slide that we have much less flows. But here, even if we increase the flow density, if you apply melting, it is even easier for flows to transverse through the strait. So here we have a lesser amount of flows, but thanks to the presence of breakage, it was possible for the flows to go through the strait. But here, with an even larger amount of flows, we can see that melting can play even a more powerful role, depending on the velocity at which it occurs, for the same type of fluid conditions applied to the flows. Now, something that we also wanted to explore was the effect of the currents and the jammed or unjammed combination that could happen at the entrance of the strait. So for example, here, if we applied a higher density field, a higher density like distribution of flows, you get some jamming if you use like a constant current. But if, for example, you introduce variations in the currents over time, you may get some temporal jams or arcs, but these arcs will break over time if sea ice was given the possibility to change positions rather than just to have like a stable granular contact configuration. So that is also something very important, because if we have changes in currents over space and time, then also the formation of these arcs can also change. So something that is also possible to measure using LS-DEM is the distribution of grain size or flow size distribution, and also to count certain sizes and how they can evolve over time. So for example, here we're just applying a constant melting field at a high velocity up to the point that some of flows are lost completely. And there you can see the changes in both flow size distribution and the count of certain sizes of flows. And this is particularly interesting because some satellite pictures and the studies of them have showed that this is effectively what happens when you have melting. You have a flattening of the flow size distribution and a decrease of the larger flows and a preference for smaller flows. And this can also be tracked for conditions where you have breakage. So here you can see how the flow size distribution starts shifting as we have breakage of some of the flows, and how the flow size count is altered by this breakage of the weakest or smaller flows. Something else to mention is that these are exactly the same conditions that I use for melting. And here you can see that if we only apply breakage, but we have a very dense distribution of sea ice, we could also get jamming. So this sort of variations are like very interesting, and I will be very interesting to keep studying them. So as conclusion for this presentation, we could see that discrete element methods that use in situ flow shapes can capture this particular granular phenomenon, such as jamming, such as the effect of flow rotations given uneven distribution of moment of inertia. Also, we were able to observe that sea ice shape, lateral melting, and breakage can affect the flow-to-flow interactions and the rate of mass loss. And though it is possible to tune the projections of sea ice mass loss, at least at the granular scale, based on this phenomena. And also, it is possible to modify our lateral melting and breakage parameters, and this is going to have a significant effect on changes in flow size distribution and the possibility of having loss or jamming through a strait. And thus, calibrating our models with satellite pictures, including this additional physical behavior, could help us capture a little bit more about the behavior of sea ice using DEM. And of course, this is the first implementation. We want to add some additional steps, such as working with flow fracture mechanics and two-way fluid coupling. So something that we want to analyze now is working with the contact loads and adding thermal stresses, fluid drag stresses, and combining all of this to get a more arbitrary stress field distribution. Because right now what we're just doing is breaking along a straight plane, but stress and damage accumulation might not necessarily result in these perfectly flat planes. And based on CI satellite observations, breakage can occur in curved, arbitrary, and irregular shapes. And this is, of course, related to the fact that shape can affect both the stress distribution, especially if we don't have a perfectly circular or square or elliptical shape. We will have stress concentrations that are going to affect both the breakage behavior, the stress, and the formation of new flows from broken ones. And for example, we decided just to study the stress evolution of this particular red flow, applying just like a large field of flows pressing against each other. And it is possible to track over time the changes of stress distribution for the flows that we desire, and apply these stress fluctuations over time to damage and breakage models. And that is something that we want to implement in the near future. And additionally, beside of the fluid to solid coupling, we want to have like a two-way coupling implementation, possibly with a resolved surface method in which the shape of the flow affects the distribution of the fluid velocities and other fluid quantities such as salinity, density. And that would like, we will have to combine a CFD mesh with our level set or our level set points. And rather than only having this direction for the effects, we will have to go in the other direction. And that is something that we are right now like currently implementing too. Like, we already have the skin drag force from fluid to flow, but we need to do the other direction of the effects. And the same will be for the form drag forces. So as we can see, there are a lot of exciting directions in which we can go. And thank you very much for your attention to this presentation. If you have any questions, comments, or if you just want to discuss in general, like how we could keep advancing with CEI's DEM and the methodologies that I have presented and that our group is working on, like, we will be very glad to talk about it. So have a nice day.